Hi everyone, my name is Jiang Zihan, metric number A220725, and welcome to my final presentation for STQM1043 calculus. My topic today is the applications of derivatives and integrals in real life. Now, calculus has a reputation for being abstract and a bit intimidating, but over the next 15 minutes, I want to show you that it's actually all around us, working quietly behind the scenes in everyday life. Let's get started. So let's begin with the big question. What is calculus? In the simplest terms, calculus is the mathematics of change. Most of the math we learn easily in school deals with fixed, unchanging numbers, adding, multiplying, solving for a single value. Calculus is different. It gives us the tools to describe things that move, grow, and build up over time. Think about the speed of a moving car, the way a disease spread through a population, or the amount of water gradually filling a tank. All of these involve change, and calculus is the language we use to describe them precisely. Calculus is built from two main tools, and the nice thing is that they are actually opposites of each other. The first tool is the derivative, which deals with rates of change. In other words, how fast something is happening at a given moment. The second tool is the integral, which deals with accumulation, how much of something builds up in total. Throughout this presentation, you will see how these two ideas work hand in hand. And that brings me to my objective for today. My goal is simple: to explain in plain and simple terms how derivatives and integrals are used to solve real problems in everyday life, using clear worked examples and visuals that you can follow along with, step by step. So even if math isn't your favorite subject, I hope you will walk away seeing it in a completely new way. Before we dive into the examples, let me put them two tools side by side, so the difference is really clear in your mind. First, the derivative. A derivative measures how fast something is changing right now, its rate of change at a single instant. If you picture a curve drawn on a graph, the derivative is the slope or steepness of that curve at one particular point. In everyday language, it answers the question, how quickly is the car speeding up? How quickly is the profit rising? The integrals is the exact opposite. Instead of looking at one instant, it measures how much has built up altogether, the accumulation over a whole stretch of time or space. On a graph, the integral is the area underneath the curve, and it answers a different question. How much in total? How much distance overall? How much area? How much water? And here's a beautiful fact that ties them together. These two operations are inverses of one another. Differentiation and integration undo each other in the very same way that adding and then subtracting the same number brings you back to where you started. That deep connection has a name. It's called the fundamental theorem of calculus. Now, with that foundation in place, let's look at each tool in real life, starting with derivatives. First up, derivatives in daily life. This half is all about rates of change and using them to find the best possible choice. So what exactly is a derivative? A derivative measures the instantaneous rate of change of something, that is, how fast it is changing at one exact moment in time, not just on average. The easiest way to picture this is with the graph on the screen. Look at the orange curve. Notice how it bends and changes direction as it goes. The derivative at any point on that curve is simply the slope of the straight line that just touches the curve at that one point. That touching line has a special name. We call it the tangent line. Now, where the curve is steep, the slope is large, and that means the quantity is changing quickly. Where the curve is gentle and flat, the slope is small, which means it's barely changing at all. So the derivative literally measures the steepness at each point. And here's a real-life example you actually use every single day. without even thinking about it. Your car's speedometer. Your speed is the rate of change of your distance. It tells you how quickly your position is changing from moment to moment. So every single time you glance down at the speedometer, you are literally reading a derivative in action. You've been doing calculus on the road that whole time without realizing it. Now, here is where derivatives become genuinely powerful in the real world. Something called optimization. Optimization simply means finding the best possible option in a situation. For a business, that might mean the maximum profit. For an engineer or a factory, it might mean the minimum cost or the least material used. These are decisions worth real money, and the calculus helps us make them exactly. The key idea behind it is wonderfully simple, and I like to think of it as climbing a hill. Imagine walking up to the very top of a hill, right at the highest point, just for a moment. The ground beneath your feet is flat. It's neither going up anymore nor down yet. The exact same thing happens on a graph. At a maximum point, the very top of a curve, or at a minimum point, the very bottom of a dip, the curve momentarily levels off, and since the derivative is just the slope, that fault moment means the derivative is exactly zero at those special points. That single insight is the key to the whole method. So to find the best option, we follow 4 clear steps. Step 1, we write down the function we want to optimize. For example, an equation for profit. Step 2, we differentiate it to find its derivative. Step 3, we set that derivative equal to 0 and solve. This pinpoints the peak or the valley. And step 4, we check whether we've found a maximum or a minimum. Using the second derivative, let's see all 4 steps in action with a real example you can relate it to. Imagine that you run a small bakery. Let's say your daily profit, measured in regions, from selling a certain number of cakes. We'll call that number x is given by this equation. P of x equals negative x squared plus 18x minus 300. The question we want to answer is a very practical one. How many cakes should you sell each day to make the most profit possible? Let's follow our 4 steps. Step 1. We differentiate the profit function to find its rate of change. The derivative, which we write as p prime of x, works out to be negative 2x plus 18. Step 2. We set that derivative equal to 0 because remember, the maximum is where the slope is flat, so we write negative 2x plus 18 equals 0. Solving that little equation, we add and rearrange, and we find that x equals 14. Step 3, we need to confirm this is actually a maximum and not a minimum. For that, we look at the second derivative, which is negative 2. Since negative 2 is less than 0, the curve is bending downwards, and that tells us we have found a maximum, a true peak. Perfect. And step 4, we find the actual profit at the point by substituting x equals 14 back into the original equation. That gives us negative 1,600 plus 3,200 minus 300, which all adds up to 1,300. So here is our answer. Selling 14 cakes a day gives the maximum daily profit of 1,300 regions. And notice the really interesting story the graph is telling us. Profit climbs steadily up to that peak at 14 cakes. But watch what happens after that. If you try to bake and sell too many cakes, your profit actually starts to fall back down again. Maybe your costs rise, or you are left with unsold stock. The point is, more is not always better, and the calculus pinpoints the exact sweet spot for us. Alright, now let's switch over to the other half of calculus, integrals. This half is all about adding up the pieces to find a total. So what is an integrate? An integrate works by adding up infinitely many tiny pieces in order to find one grand total. It's the mathematics of accumulation of things building up bit by bit, and on a graph, integrating a function gives you the area underneath its curve. You can see this idea on the screen. That shaded teal region sitting under the curve represents the total amount we are adding up. Here's the clever part. Imagine slicing that whole region into a great many very thin vertical strips. Each strip has a tiny area, and if you add up the areas of all those strips together, you get the total area. The integral does exactly this, and it does it perfectly, giving us the precise total rather than just an estimate. Let me give you a simple everyday example. Filling a water tank. Suppose water is flowing into a tank. If you add up how much water flows in during every single second, the running total tells you the total number of liters collected. That accumulated total is precisely what an integral calculates. In fact, almost anything that builds up gradually over time or over space, distance traveled, water collected, energy used, or cost accumulated can be measured using an integral. Let's walk through a real example together. Suppose a car is speeding up and its velocity, its speed in meters per second is given by the equation v of t equals 10 plus 4t, where t is the time measured in seconds. Our question is, how far does the car travel during the first 5 seconds? Now, distance is the accumulation of velocity over time. So to find it, we use an integral, and remember what that means visually. It's the same as finding the area under the velocity time graph. So we integrate the expression 10 plus 4t from time 0 to time 5. Let's do it step by step. When we integrate each term, 10 plus 4t becomes 10t plus 2t squared. Next, we substitute in our limits and t equals 5. We get 10 times 5, which is 15, plus 2 times 5 squared, which is another 15, giving us 100, and at t equals 0, everything is just 0. So the total is 100 minus 0, which is 100 meters. And here's a lovely way to double-check our answer using simple geometry. The shaded area under that straight line is just a trapezoid shape. Using the trapezoid area formula, 1/2 times the sum of the two parallel sides times the width, we get 1/2 times the quantity 10 plus 30 times 5, and that also works out to exactly 100. So both methods agree completely. The car travels 100 meters in the first 5 seconds. The calculus and the geometry give us the very same answer, which is always a satisfying sign to say. Now, those were just 2 examples, but I really want to drive home the point that calculus is genuinely everywhere, across almost every field you can think of. On the derivatives side, remember that's all about rates of change. We use them constantly. We use derivatives for speed and acceleration when driving, for finding the best price or the best output level in business, for measuring how quickly a population grows or how fast an infection spreads through the community, and even for designing safe slopes and gradients on roads and wheelchair ramps so they are not too steep. And on the integral side, all about adding things up, we use integrals to calculate areas and volume in construction and land surveying, to find the total distance traveled from a changing speed, to work out probabilities in statistics, which is really the area under the famous bell curve, and to measure accumulated totals. like the total water, energy, or cost that builds up over time. It's the same two tools used over and over in field after field. So let me bring everything together. Today, we explored two powerful tools at the heart of calculus. Derivatives measure rates of change, and they let us find the best option through optimization. Remember our bakery, where selling exactly 14 cakes a day gives a maximum profit of 1,300 regent. Integrals add up many tiny pieces to find a total, which on a graph is the area under the curve. Remember our car, which traveled exactly 100 meters in its first 5 seconds. And the big takeaway I want to leave you with is this. Calculus is essential for solving real-world problems. It is so much more than abstract symbols on a page. It is the hidden engine behind driving, business, construction, medicine, and countless other parts of daily life. Thank you so very much for watching my presentation.